Okay, so welcome back, and let's continue the discussion on the piston and propeller engine. And we have talked about what is the basic engine type and their arrangements and all this. So we just started taking the assumption for reciprocating engine, and now we will look at the thermodynamical analysis of those engines. So this is what we have talked about, this air standard. For air standard analysis, the assumption and things like that, and then what we will do, we will talk about two cycles here. One is the Otto cycle and another one is the diesel cycle. So, Otto cycle is for spark ignition engine and this one for the compression ignition analysis. Now, there are specific heats of air are function of actually temperature like Cp and Cv, and the temperature within the cylinders actually vary a lot. So, and also the ratio of the specific heat is gamma, which is, so the to simplify the analysis what we will do. So, that means in cylinder, in realistically Cp, Cv they are function of temperature. So, gamma also becomes function of temperature or something like that, but to make it simple for simple analysis, we will say gamma to be constant, and we will use some average value of 1.35 and something like that, and also we will use the constant Cp value, which is something like 1.108 kilojoule per kg Kelvin, and Cv is 0.821 kilojoule per kg Kelvin. So, R would be Cp minus Cv, which is 0.287 kilojoule per kg Kelvin, and gamma is Cp by Cv is 1.35. So, these are what we are going to use. So, let us start with the Otto cycle, and first this is a cycle for the spark ignition engine. So, this was named in after Nicholas Otto, who built 1876 I think a 4-stroke engine and successfully in Germany. In most spark ignition engine or SI engine, the piston executes 4 complete stroke, 2 mechanical within the cylinder, and the crankshaft completes 2 revolutions. So, these are called 4-stroke internal combustion engine. So, the typical PV diagram. So, let us say this is a state from where it goes here, that is state 0 or TDC. Then from here this goes like this, then this, then like this, and comes like that. So, this is 1, 5, 2, 3, 4. So, this is where heat is out, combustion in, then this process is isentropic, and that is same for this guy also, and this is the bottom dead center. Okay. And then same thing if you put back in the TS diagram, this is 2, 3, 4 like this. So, 1, 5, 2, 3, 4. So, this is V constant process where Q in, V constant process Q out. So, this is the PV and TS diagram. Now, first between 0 1 process, say this is a constant pressure intake stroke. So, and the pressure at the intake takes place at P naught. With the intake valve open and exhaust valve closed, the piston makes an intake stroke to draw a fresh charge, and it could be a mixture of fuel and air for SI engine into the cylinder. So, what it gives, P 1 would be P naught. So, let us say W 01 would be P naught V 1 minus V naught. Here this one is the V is specific volume. Okay. So, now move to process 1 to 2, that is isentropic compression stroke. So, with both the valves closed, the piston undergoes a compression stroke and raising the temperature and pressure of the charge. So, this requires an input from the piston to the cylinder. So, what happens, T 2 would be T 1 V 1 by V 2 gamma minus 1, which is T 1 V 1 by V 2 gamma minus 1 T 1 R C to the power gamma minus 1, and P 2 is P 1 V 1 by V 2 gamma, which is P 1 which is to the power gamma P 1 R C to the power gamma. So, what we have, the specific work output would be P 2 V 2 minus P 1 V 1 by 1 minus gamma. So, we can replace that with R T 2 minus T 1 divided by 1 minus gamma, which is U 1 minus U 2. This is change in internal energy or delta U C B T 1 minus T 2. Now, the process 2 to 3, this is constant volume heat addition process or the combustion. So, here what will happen, we will have the T 3 would be T max, P 3 would be P max, V 3 would be V 2 V T D C, and 2 to 3 would be 0. Now, specific heat is added, that Q dot in. So, Q 2 to 3 is Q in, which is C V T 3 minus T 2, which is U 3 minus U 2, and the Q 2 to 3 it Q in, which is m dot F Q heating value into eta C, which is m dot F C B T 3 minus. So, let us say m dot M, which is mixture. So, that we can write m dot A plus m dot F into Cv T3 minus T2. So, what we can write, the Q heating value into eta C would be air fuel ratio plus 1, which is 1 plus F Cv T3 minus T2. So, here QHB is the heating value of the fuel and AF is the air fuel ratio. So, which is m dot A by m dot F. So, now after this combustion, what will happen? The gas mixture will leave having the maximum pressure and the temperature. So, this will be towards the end of the compression stroke. Now, the fourth stage, this is process 3 to 4, which is again an isentropic power or expansion stroke. Okay. Now, it follows the compression stroke during the gas mixture expands and work is done and all the valves are closed. So, what we get, T4 is T3 V3 by V4 gamma minus 1, T3 V3 by V4 gamma minus 1, T3 RC gamma minus 1. Same way we can write P4 equals to P3 gamma V3 by V4 gamma RC to the power gamma, and Q34 is 0. So, the specific work in 3 to 4 is P4 V4 minus P3 V3 1 minus gamma, which is T4 minus T3 1 minus gamma. So, you can write Cv now. We have process 4 to 5. This is again constant volume heat rejection process or sort of exhaust blowdown. Now, the exhaust valve is open and intake valve is closed. So, we get V5 is V4 is V bottom dead center and this would be 0. Here specific heat rejection is Q out. So, Cv minus T5 minus T4, T1 minus T4, which is U5 minus U4. So, Q4 minus 5 is Q out, m dot m Cv m dot m Cv T1 minus T4. Now, we have the last process, which is 5 to 0, which is again constant pressure exhaust stroke at P naught, and the piston executes an exhaust stroke in which the burned gases are purged from the cylinder through the open exhaust valve. So, here we have P5, which is P1 and P naught, and specific work is P naught V naught minus V 5, V naught minus V 1. So, we can find out the thermal efficiency of the Otto cycle. So, thermal efficiency of Otto cycle. So, since the Otto cycle is executed in a closed system, we can disregard the changes in the kinetic and potential energies. So, the energy balance could be written like W net is Q in minus Q out in terms of kilojoule per kg, with W net is Q in minus Q out, which is U 3 minus U 2 minus U 4 minus U 1. So, the thermal efficiency of Otto cycle is defined W net by Q in, which is 1 minus Q out by Q in, 1 minus U 4 minus U 1 by U 3 minus U 2, 1 minus C V T 4 minus T 1 by T 3 minus T 2. So, what we get 1 minus T 4 minus T 1, T 3 minus T 2, 1 minus T 1, T 4 by T 1 minus 1 by T 2, T 3 by T 2 minus 1. Now, since the process 1 to 2 and 3 to 4 are isentropic and V 2 equals to V 3 and V 4 equals to V 1. So, what we can write T 1 by T 2 is V 2 by V 1 gamma minus 1, which is V 3 by V 4 gamma minus 1, which is T 4 by T 3. So, we can rearrange that like T 4 by T 1 is T 3 by T 2. And now, if we put this back here, again what we get 1 by R C to the power gamma minus 1, where R C is V 1 by V 2, that is V max by V minimum. So, thermal efficiency is dependent on the compression ratio and obviously the heat ratio. So, if you plot that for different heat ratio, like this is let us say 2, 4, 6, 8, 10, 12, 14, 16, this is R C and this is eta T H, this is 0.1, 0.2, 3, 4, 5, so like that. So, it goes like that. So, it just different values of gamma if you increase that. This one start with 1.3, something like that. So, that is a typical curve that one can see. So, from here one can what one can see that the thermal efficiency curve is steep at low compression ratio, but flats out when starting with a higher compression ratio beyond 8 or something like that. So, the increase in thermal efficiency is quite with the compression ratio is not a pronounced at high compression ratios. That means, when you go beyond certain compression ratio, it not necessarily that efficiency will increase further, but at the lower RC, as we increase it, it increases. Now, for a particular given compression ratio, this is let us say gamma 1.4 and gamma 1.667. So, the monoatomic gas like argon or helium, they will have the higher thermal efficiency compared to the heat ratio of 1.3 in the same. Now, typically the working fluids in actual engine contains larger molecules such as carbon dioxide, and the specific heat ratio also decreases with temperature, which is one of the reason that actual cycle will always have lower than the theoretical ideal Otto cycle. Second, for a given compression ratio, the thermal efficiency of an actual SI engine is less than that ideal Otto cycle due to irreversibles. That is obvious, because what we have got here is the ideal one, but theoretical one, but actually there would be irreversibilities, and typically the SI engine efficiency would be about 25 to 30%. Now, we can find out now power generation and fuel consumption. So, the torque generated in the piston engine is normally measured with a dynamometer. The engine is clamped on a test bed, and so the torque, which is this is the torque exerted by the engine, is F into B. So, the power which is delivered by the engine and absorbed by the dynamometer is, let us say this is the power P is T cross omega, which will be 2 pi n T. So, now one can find that this is force F into B torque. So, the value of the engine power is called the brake power, which is P B, that would be 2 pi n T into 10 to the power minus 3, which is kilowatt. So, the indicated power is correlated, and you can see in a area diagram of a PV area diagram. Let us say this is what happens at the intake stroke, then it goes back here, goes like that and comes like that. So, this is bottom dead center, top dead center, this is exhaust, this is intake. So, what happens? So, this is, let us say this is area A, this is B, and this is C. So, you can see how the power is the indicated work per cycle per cylinder WCI, which will be PdV, and the net indicated work per cycle of the cylinder, which is area A minus area B. Then the power per cylinder is related to the indicated power. So, per cylinder would be indicated per cylinder, indicated power WCI into N by NR, where NR is the number of crank revolution. For 4-stroke engine, NR equals to 2 for 2-stroke engine. So, this is 2 for 4-stroke, 1 for 2-stroke engine. Okay. So, this power is the indicated power, and then what we get, WCI is Pi NR by N. Now, for 4-stroke engine, this is WCI is 2 Pi by N, and for 2-stroke WCI is Pi by N. Now, the brake power can be related with the indicated power. So, indicated power is the brake power plus PF, and PF is the power consumed in overcoming the friction of the bearing. So, driving accessories, induction, exhaust and stroke. So, this is the power which has been used to some of these things to operate. Okay. So, and then eta mechanical efficiency would be ratio of brake power by indicated power. Typically, this is around 90% for modern automotive engines, where the revolution is around 1800 to 2400 RPM, or 75% for the maximum speed limit. Now, there would be another parameter which to describe these engines are the MEP, which is mean effective pressure. So, the mean effective pressure is the fictitious pressure that if it is acted on the piston during the entire power stroke, it produces the same amount of net work that produced during the actual cycle. So, which means W net would be MEP into piston area into stroke. So, that is MEP into displacement volume. So, MEP would be W net by displacement volume, which is V max minus V min, which is in W net V max minus V min. So, one can see in a PV curve like this, where let us say these are the two ends. So, the cycles lies there. So, here it goes, comes back. So, that is W net, and this is MEP, and this, if we look at the so this is TDC, that means V min, this is V max. So, this is M EP into V max minus V min. So, that is also W net. So, this area, and this is where the cylinder lies. and that is the bottom dead center. So, this is BDC. So, various mean effective pressure can be defined using in terms of like if it is indicated work, then IMEP, it is indicated mean effective pressure, which is W CI by VD. So, we will kind of using this mean effective pressure, you can define the other parameters, and we can look at those details in the next class.